Dear students, in the last class we had seen about the application of elastic property of a particular material. Okay, there we had seen the elastic property, the application of elastic property in the making of rope for the crane. Then we have also seen something about the bending of bridges due to the heavy load. Then we had seen how to estimate the height of a mountain, why the height of the mountains on earth are restricted to certain height, like the maximum of 10 kilometers, and why it cannot be beyond that. Okay, so that is due to the elastic property of the particular materials. Now today we will see some important definitions. Okay, there is a chance of getting these definitions for 1 mark. The first one is about buckling. So we had seen this term in the last class. Buckling, it's a simple phenomenon where when load acts on a particular bridge, okay, or we can say the pillar of the bridge, what actually happens is it gets bent like this. Correct, right? So it bends like this. So this phenomenon of bending of the bridge, okay, or the pillar of the bridge under load is known to be buckling. Okay, definition says bending of beam under a load, that is known to be buckling. It's a very simple definition. Next one is about elastic fatigue. So you must have heard about fatigue, like after you do so much of work you'll get fatigue. Correct, right? Similarly, the elastic fatigue is a word which tells you it's about the temporary loss of elastic property due to continuous strain in a particular material. So we can take the example of the bridge. So if you consider a bridge, you know that the bridge has got a lifetime. So maybe some 100 years or 50 years will be given as a lifetime for a bridge once it is constructed. So why it is given the lifetime? Because you know that the bridge will be always under particular amount of load continuously, right? Because all the vehicles will be moving on the bridge. So when the vehicles move on the bridge, what actually happens? There is a slight strain happens to the bridge. Okay, you can understand that you must have experienced it, slight shaking of the bridge when a heavy truck or something passes through that, passes on that. Okay, so slightly there is a bend. Okay, if it is a straight, it will bend slightly. After that it will again regain its original position once the vehicle passes over there. Now if the process continues, like continuously, if the body is under particular load, what actually happens after a long time, it will lose its ability to regain the original dimension immediately after the load is removed. So that temporary loss of elastic property due to continuous strain is known to be elastic fatigue. Okay. Next one is also a similar word. It is elastic after effect. So here in the previous one, elastic fatigue, what actually happens is the ability of getting the original dimension is temporarily lost. Correct, right? Here also it is a delay in regaining original state on removal of deforming force on a body. So here what happens, the same effect whatever we have explained for elastic fatigue, it also applied to this one. So when a load is applied on a particular material, it undergoes strain. Okay, once a load is removed, it takes more time than the more than the usual time to regain its original dimension. So that delay is known to be elastic after effect. So these are simple definitions, may be asked for 1 mark, you can expect it. Next one, bit important on the basis of NEET or CET, Poisson's ratio, and also there is a chance of getting this for your 1 or 2 marks. So Poisson's ratio, it is very simple. It is the ratio of lateral strain to the longitudinal strain. Okay, it is a ratio of lateral strain to the longitudinal strain. So within elastic limit, the ratio of lateral strain to longitudinal strain is called Poisson's ratio. So we will mention everything within the elastic limit. So this ratio is known to be Poisson's ratio. Now what is this lateral strain? If you consider a wire, okay, so we are considering a wire. Now it has a dimension, correct, right? when I increase the length, what actually happens to the dimension? See, if I stretch this one, okay, if I stretch this one, then its dimension, what you see here, is going to get decreased. Correct, right? Why? Because whatever dimension over here will be changed into the length. So what actually happens here? Once there is a longitudinal strain, okay, longitudinal strain, you know, it's already delta L by L, change in length to the original length. Okay, once a body undergoes longitudinal strain, there will be a lateral strain as well. So lateral strain is nothing but change in its dimension, so that is this one, okay, to the original dimension. Okay, change in dimension, that is, you can take it maybe the radius or diameter, whatever, to the original one. So this ratio is known to be lateral strain, and this ratio with the longitudinal strain is known as Poisson's ratio. And you can see here there is a negative sign. So what does this negative sign indicates? You can see once the length increases, what happens to the dimension? See, if I take the radius, obviously radius has to decrease. So negative sign indicates that longitudinal strain and the lateral strain are in opposite sense. So if I say that longitudinal strain like a length increases, then it is seen that the radius is going to get decreased. Okay, so this is about Poisson's ratio. The next term what we need to study here is about elastic potential energy. So it is the energy stored in a stretched string. So you know about two types of energy, that is potential energy and kinetic energy. No, right? So when I hold this pen, okay, over here, then I can say that it has got potential energy, that is nothing but U is equal to M, okay, G and height H. Then if I throw it, then it will have kinetic energy, that is half mv square. Similarly, when a string is under strain, or we say that when it is under some stress, okay, it is going to have certain energy stored in it. So that energy is known to be the potential energy of a stretched string. So we can write this potential energy, that is nothing but half into stress into strain into volume of the wire. So this is the equation for elastic potential energy. Then potential energy per unit volume, that can be written as simply the we are just avoiding this term, volume of the wire, then we have U is equal to half sigma into epsilon. Okay, so that is nothing but stress into strain. Then you don't need to worry about these notations. So this notation was actually mentioned for the stress, then here it is also mentioned for the Poisson's ratio. So there is nothing to do with the much about these notations. You can write what is this actually. So if you are writing this equation, here you can just mention it. Okay. Next one, we will see some simple problems. Then actually the problems will not be asked for the examination, but we don't want to take a chance if there is any chance of getting a problem. And even if I solve some problems, it will help you for your NEET or CET also. Okay, so we will solve some simple problem first, then we will go to the somewhat higher level problem, or finding more than one term. So this is a simple problem. Here, a steel rod of area of cross section 3.14 into 10 to the power 4 Newton meter square, okay, is stretched by a force 100 kilonewton. Calculate the stress acting on the rod. So what you need to do is you have to find out the stress acting on the rod, which is stressed by a force of 100 kilonewton. So you are given all the terms. Okay, what is force? It is given to be 100 kilonewton, right? So kilo is nothing but 10 to the power 3. So 100 into 10 to the power 3 we'll have to write. Then what is area of cross section? It is also given. We will simply substitute this one, 3.14 into 10 to the power 4. So you can do the calculation, okay, and finally you will be arriving at this answer. You can check it for yourself. Okay. The next problem, it is about a square lead slab of side 50 centimeter and thickness 10 centimeter subjected to a shearing force of 9 into 10 to the power 4 Newton. Calculate the shearing stress acting on the slab. Okay, so what you are given? You people are given with the one side it is 50 centimeter, then thickness is 10 centimeter. Okay, now what we need to find out? We have to find out the shearing stress. So shearing stress is nothing but shearing force by area. Okay, now we need to know what is shearing force. It is already given over here. We can write 9 into 10 to the power 4 Newton. Now area of a slab, so that we need to take the length into height or the side, whatever we can take, length into breadth we can take. So what it will be, we are given with the side it is 50 centimeter, then thickness 10 centimeter. So centimeter has to be converted into meter, you know right how to convert it. So 50 will become 0.5, 10 will become 0.1. Now multiply them both, okay, multiply them, then what do you get? 0.05 meter square. Now substitute the values over here. You can substitute shearing force 9 into 10 to the power 4 divided by area 0.05. So do the calculation and you will be going to arrive at this answer finally. You can check this answer. Okay. Okay, let's see the third problem. It is a board. A steel rod of radius 10 millimeter and length 2 meter is stretched by a force 100 kilonewton along its length. Now we have a wire, or we can take it as rod over here. Okay, so the dimensions are given. It has radius, it's given as radius 10 millimeter, okay, and its length is 2 meter. Now it is stretched by a force, okay, that is equal to 100 kilonewton. Okay, now the elongation in the wire is 3.2 millimeter. Find the stress and Young's modulus of the material of the rod. Now what happened? Once this rod is stretched by a force of 100 Newton, there is a slight elongation, that is nothing but delta L, which is given over here. It is 3.2 millimeter. Now we have to find out the stress acting on the rod as well as Young's modulus of the material of the rod. Okay, first we will find out, first we will list out the things whatever given here. Radius, it is given as 10 millimeter. Force is given, it is 100 kilonewton. Length is given, it is 20 meter. Then elongation is given, that is 3.2 into 10 to the power minus 3 or 3.2 millimeter. Now how to find out stress? We know already stress is nothing but force by area. So as it is a rod which has a radius, we have to take area is nothing but pi r square. We know the value of pi, we know the value of r, then we know the value of f as well. Now substitute. Okay, f is nothing but 100 kilonewton, pi 3.14, r is 10 into 10 to the power minus 3 square of that. So do the calculation. Okay, you can do the cancel the powers, then finally answer will be 3.18 into 10 to the power 8 Newton per meter square. You can check the answer. Next, what we need to find, once you find stress, you can find out Young's modulus. So how to find out Young's modulus? It is nothing but stress by strain, or we have seen it as like longitudinal stress by longitudinal strain. Now stress value we have calculated from this one. Strain, we can just do this one like delta L by L. So what happens to this L? L actually goes to the numerator. Then we will substitute over here. It is nothing but 3.18 into 10 to the power 8 divided by 3.2 into 10 to the power minus 3. It is elongation multiplied by length, that is 2 meter. So why we are multiplying this value whatever given with the 10 to the power minus 3 is to convert into SI unit. Now once you do this calculation, the final value what you are going to arrive will be 1.98 into 10 to the power 11 Newton meter square. So Young's modulus has got the value SI unit, which is same as that of stress, because strain doesn't have any unit. So you can do this calculation. Okay, it's a very simple one. Then try to get this answer. So don't copy from this board. You can just substitute the values accordingly, and you can do the numerical calculation using your calculator. Then finally arrive at these answers. Next problem. The upper face of a cube of edge 1 meter moves through a distance of 1 mm relative to the lower fixed surface under the action of tangential force 1.5 into 10 to the power 8 Newton. Calculate tangential stress and rigidity modulus. So this is like a problem what you can consider here. There is a cube over here. Now what actually happens here? Upper face, you are applying a tangential force. So upper face will get shifted with respect to the fixed lower surface, or upper surface gets displaced with respect to the fixed lower surface. Now values are given. What all things are given? Delta x, that is nothing but, like if it is like this, you have seen this is delta x, correct, right? Okay, so delta x value is given, what it is, 1 millimeter, correct? 1 into 10 to the power minus 3 meter. Now length of the side, it is given 1 meter, correct? Then we are also given with the force that actually happens, gets applied over here. Now what we need to do? We have to substitute the values and find out shearing strain first. Okay, now how to find out shearing strain? It is nothing but delta x divided by L. We have the value of delta x, that is nothing but 1 millimeter. We have the value of L, that is 1 meter. Simply substitute and you will get the answer 1 into 10 to the power minus 3, or simply 10 to the power minus 3. After getting the value of this strain, next we will find out what is tangential stress. So tangential stress is nothing but tangential force by area of the face. Now we are given with the value that the tangential force, it is given over here 1.5 into 10 to the power 8. Okay, then what is area? Length into breadth. So if you take this as L into L, what do you get? You will get as 1 itself, correct, right? So we will write it as 1 over here. So tangential force 1.5 into 10 to the power 8 divided by 1. You will get the same value. Now what we need to find out next is about rigidity modulus. Okay, once we have both these values, that is shearing strain and the tangential stress, we can find out modulus of rigidity or rigidity modulus. We will substitute this stress divided by strain. So what is the value of stress we got? 1.5 into 10 to the power 8 divided by strain value, it is 10 to the power minus 3. Now you can take this term to the numerator, then what happens? It becomes 10 to the power 3, 10 to the power 8 plus 10 to the power 8 into 10 to the power 3. So 8 and 3 gets added up, you will get 11, and 1.5 divided by 1, it's nothing but 1.5 into 10 to the power 11 Newton meter square. Okay, so these are the problems. So there is a chance if you get the problem, then you can solve this. Then I'll give some more problems on the assignment part. Okay, so this is the end of this chapter. Next we will see about the mechanical properties of fluids.